Okay, let's get going. Welcome everyone to day 4 of the StatEase 2025 Online DOE Summit. I'm pleased to see so many familiar faces back again in the attendee list. Uh, and it's we're here for another wonderful talk today. Niels Dekker is here from AkzoNobel to tell us about his actual case study using DOE and StatEase software. Um, I don't have much more to say about it than that. So, Niels, it's all yours.
Good. Thanks a lot. Good morning, good afternoon, and good evening, everyone. My name is Niels Dekker. I'm very pleased to be one of the presenters on this online StatEase DOE Summit. We already had some great presentations over the last few days. So I want to continue with having a look at some tips and experience-based insights into DOE, which I will give using the example of our coatings industry business on robotic coatings application. So first here you see my bio basically. As you can see, I have I have a degree in statistics from the University of Amsterdam in the Netherlands. Spent my whole life in data analysis and most of it in DOE. I graduated in mixture designs, and for the last few years moved into the management team of AkzoNobel, but kind of came back, still a manager, but now more hands-on back into data analysis, DOE, automation, digitalization, and other good stuff. But as you can see, I spent quite a lot of my career, still am, in design of experiments. And I wanted to start off with saying that I have not always been true to what I was taught during my education. And I kind of want to highlight that and show that based on an experiment, that one of the experiments we've been doing here at AkzoNobel that I will discuss in this chat. So I will first touch on why I think this is important to deviate sometimes maybe a little bit from the theory that is written in the books and in other resources. And I will do that using the example. But also please keep in mind that in the previous webinars that I saw, not this week, but also ones from earlier this year, as well as by an article by Peter Goos on the Omar's designs. It was a very important statement made that the theory is great, but that there are other things at play that drive the experimental strategy choices that you make. And that's something that I want to continue a little bit on. But first, because of course we are also here to celebrate 100 plus or around 100 years of DOE and 40 years of StatEase, I want to kind of touch very briefly on a few highlights in my pretty long DOE career. First, design expert. Yesterday I was in the presentation of Martin Briesner, the CTO of StatEase, who was talking about the different versions of StatEase. I think Alpha Design Expert. I think I stepped in version 6 or 7. I don't have files from that anymore, but that kind of related to the history that he talked about. I've attended many face-to-face meetings from the StatEase face-to-face user meetings in the past, and the one that always springs to mind is the one in Cambridge where we did a beer experiment that was organized by the Prism company, which was probably one of the best applications of mixture designs that I've ever attended. And then my favorite tool in explaining people DOE training sessions that I have been given over quite a lot of years. My Statipult that I trust dearly, of course, also for DMIC, Six Sigma type of things, but DOE, it's really fun to use it and to have people play with it around on the factors that they can change. But kind of this all ends up to all the celebrations and the good stuff that we achieved in AkzoNobel, but also even when I was doing my thesis at General Electric Plastics with DOE. I can honestly say that I don't think I would have been in the position where I am now without DOE. It really drove my career also through the years at AkzoNobel. So enough of that. Let's move into what I wanted to to really come and state. This is one of my favorite quotes. Theory guides, experiment decides. Typically generated, attributed to Goldhoff. Really like it next to work smart, not just hard. That's one of my other favorite mottos. And I fully agree with it, that theory, that in the end, the final decision should be made by experiments. But next to fear, I think prior knowledge in the area of what you're working in is really important to come to the right experiments that and indeed will drive the decision that you will have to make. So it will then reduce further the amount of samples that you need to do, of the test work that you need to do, and to really contribute to the other motto that I have, like I said, work smart, not just hard. But I think this also applies to design of experiments. So actually, the motto that drives design of experiments actually works on design of experiments as well. Um, the theory is not leading. It's a guide, and there are other requirements in the end that decide. So, for example, you've got non-simplex design spaces, design space restrictions. This is the middle, the green graph is actually a part of the Statopult experiment that you can do, where some of the combinations are actually impossible to shoot. Um, so there also you have that, but also again the prior knowledge that really plays a role in how the experiment should be run, which samples to do, how many samples you actually need to do, which models you would assume, etc., etc. And as I already referred to, as by Peter Goos, who also stated that in the Omar's article, one big thing in, of course, in industry is time to market. Speed of delivery is humongously important. Otherwise, you will just end up at the back of the line in your innovations and product developments. Um, and all that together makes it really important to deliver fast results based on efficient but still sturdy and good experiments. And that typically ends up to be optimal custom designs, definitive screening designs, and although maybe less well known at this moment, still the OMAR's design, the orthogonal minimally alias response surface designs that are coming up in the experience. And it's not just that it's important for the company from a business perspective, but it's also very important to get the buy-in from scientists that work in other fields in the company. For example, more chemists and physicists in my case, to kind of bring them to the power of DOE, to make them understand what DOE can do, um, and to actually meet their needs and solve their challenges. We have a lot of new people in our company that come in from university or other companies that have done some DOE courses, typically some basic stuff, and they really come in and say, well, DOE doesn't apply to chemistry or to formulations, for example, because they are kind of restricted in the knowledge they have, and so it's really important to expand that knowledge into the more complex or non-standard designs that are available, of course, in Design Expert, but also in other software packages. So in this case, in the case that I'm discussing here, the example, I will show that I will kind of show this as in our industry as an example where we decided to not always follow the lines that indeed, like I said, I was taught to when I came from university, and some of the information that you being taught during courses, of course. But to do that, I first want to go high level over the process that is very important in the industry that I work in the vehicle refinish process. So let's say that you unfortunately made a dent in your car by hitting a little post or scratching a bike or whatever might have happened. So you got a little scratch. And so you bring it to the body shop for repair because, of course, you are proud of your car. You want to keep it nice and stop it from rusting. So it goes to the body shop, and the body shop will first dent it out if necessary, and then we'll start to prepare the spot where the dent was. Then after that, the body shop will start spraying the different layers of the repair system. And that is very important to understand that the repair system, the repair paint system, is very different from the original paint that the original car manufacturer actually put on the car. But to be able to do that, the body shop needs to be able to find and put on, of course, the right color, so that and when the repair is done, the car comes out of the body shop owner is happy with the result, and you as car owner are also happy with that result. Now this repair paint typically consists of three layers. You've got a primer sealer layer, which also helps to stop corroding your car further, of course. Then you have actually the first visible layer, which is the base color layer. So that's where the color comes from typically. And then the last layer is the clear coat layer, which is more the protective layer in most cases to protect the base color layer from small scratches and problems. This base coat layer is typically applied in two layers. But as I said, because this repair system is different from the original paint system that car manufacturers put on your car, it is very important and it's quite a lot of work to make sure that you get your right color so that the matching of the color, so the color that the paint that will be put as a repair paint on the car is the same color as the paint that is actually already on the car. It's actually quite complex and yeah, if you don't properly think about it, you might think it's not as difficult, but it's actually a very intrinsic process where efficiency, of course, like everywhere, is key. So the first thing you need to do is you need to get a representation of the color that is on the car already. You can do that by a measurement. There are different spectrophotometers in the market that can do that for you. Will get you a digital representation of the color. You can take a swatch, like in the do-it-yourself shop, like there are available for the decorative paint, of course, but those are also available still for car colors. It might be that your car went to the body shop there already before for a previous scratch, for example, and they have a little swatch or little spray out of the paint that they use then. And you have the VIN number, the vehicle identification number in your car, which also contains information that can be turned into representation of a color. Then that color, so the representation, needs to be turned into a formula so that you can actually mix components together to make that color. Well, that can come from databases, search engines, models, optimizers, all kind of good stuff that we have to help the body shops to do that. And the last option is an own bank, and that refers to the previous visit. If they have a little spray out of the sample that was made during a previous visit, typically these samples are stored, and so there is a formula available for them as well. And of course, then the next step is to actually make the paint. So you have toners in the formula. So you have a blue toner and a red toner and a white toner and a black toner, etc. And they are mixed together in the right amounts to create the formula. So that's weighing and mixing, of course. And then that car color needs to be applied on the repair part, actually. But to be able to do that, of course, for any car that might come into the body shop, because not all cars are black, as Henry Ford once well, wished, I could almost say. We have an endless amount of colors on the road. The one blue is not the other blue. And so we need to be able to, of course, match all these colors that are out there on the market in an efficient way. And to do that, you need to make color samples during your research of this new base color layer that you are preparing. Um, and so these samples together then with colorimetric toolboxes, digitalization or automation approaches, modeling, all kinds of tools, we are able to turn those subset of colors into the whole gamut of all colors that are available in the market via clever, mainly it's modeling and digitalization and automation approaches. And as you can see on the left, over the years, we have managed to reduce the number of color samples that we need to put into these tools, the models and the theories to further reduce that. But so it still means that you need to create a set of color samples. It's not that you can just theoretically come up with all those formulas. That's impossible. And so to be able to do that, you need to make these samples, and those samples are not made by hand because for accuracy and repeatability reasons, we like to make those with robots, also speed, of course. But then if you do that with robots, with robotic application, it's of course very important that what you make with the robotic application in a lab, in a color lab as we have them here, that is mimicking what the manual application is coming out with. So that if indeed that color there, that formula is then sprayed in a body shop somewhere by hand, that it gives the same properties, especially in layer thickness and color, as when you spray it with a robot. And so to do that, how that process kind of works is that we first have our application and product experts to, based on the development of the product, already bring and start to work on a robotic program. They have knowledge about that, and in a relatively very short time, they get the color and the requirements already pretty close to what we need, so mimicking the hand application. They then we talk with them and they supply us with relevant factors and the ranges of the factors that they think will deliver the right application program. And then you need someone who has DOE expertise so that, and not just based on what we have now and the theoretical designs that are available, but also based on prior knowledge of similar experiments, whether it's on color or on application, and a little bit of understanding about color and the product. I think that is important to be able to build strategically right and effective designs. And then the knowledge about the optimal designs that are there, that then indeed the design can be created in the right way to drive efficiency and speed to market also for the company. So in this case, um, like I said, the base coat, the base layer typically is applied in two layers. So for each layer, the robot, in this case, we could vary 4 factors from low to high. So 2 times 4 is 8 factors already. Then we have the time that you wait between layers. And then we had 2 different gun types. So we had 2 different spray gun types that we could use that are typically used on robots. So those we also took into account into the design. And what is always useful, and I will come back to that, is to add some verification runs, which were based on the work that the application experts already did, so that we could kind of check whether that was consistent with what they were already what they already had been doing. And it gives you, of course, samples to be able to verify the models that you have built using the optimal design that we would select. So then when you get started, you think about, so I have a good overview of the number of factors and ranges and stuff like that. And then you think about, so what design type could I do? Well, of course, it is response service based with numerical factors, categorical factors. So central composite design would, for example, be a way to go. For a full central composite design, with the 9 numerical factors and the 1 categorical factor that we're dealing with, you would come to about 1,000 samples. You can do a full quadratic model with some third order terms in the categorical factors. And that's how the CCD is set up. And of course, the good thing about these type of designs is that the fifths, so the orthogonality is great. So fifths of 1, almost all. And so that means that all the factors in the model terms are fully orthogonal. That's of course great, but it's quite a lot of samples to do. You could look at the minimum resolution for design that is also available for 140 samples. The fifths are still good because balancing fifth orthogonality for less samples is kind of basic business in our industry. And also you could have a look at the box Banken design. In this case, would approximately come to 260 samples. That's all good, but of course, like I already said, typically we also directly start looking into custom designs for a full quadratic model. And in this case, you would end up with approximately 75 samples. and because of all it's not a restricted design space, the fibs would still be very low. So orthogonality is not full, but still close. And so, given the amount of the sample reduction, this would probably be an option that we could do. But there is another option: definitive screening designs. It has some restrictions. We'll talk about that in a little bit. But it could do main and quadratic effects, and for large interactions, it can do a good indication uh, whether they are significant or not, and whether they help your model or not. In that case, we would come up with about 24 samples, and the fibs for the main and the quadratic effects are very low. And the good thing about the definitive screening designs is that you can add a dummy factor or two or three to increase the model accuracy if you think that you could use a few samples. Also, additional samples, like with any design, basically, it's always good to add so that in case something goes wrong, one of the samples fails, whatever you might occur, things happen, that you're not directly stuck um, and can't do a decent analysis anymore. So just a little bit about definitive screening designs, because of course the low number of samples looks then very attractive. There are many literature papers written. Design Expert, of course, has information about these type of designs as well. So widespread usage, but you have to handle them with care. And so they are mainly used for to estimate main and quadratic effects. Um, the main effects are not confounded with interaction terms. And the good thing is that's one of the big benefits is that you can always reduce the design if you find out the models to a quadratic model in any less or equal than 4 factors. So any 4-factor combination from your total set of factors will always be able to do a full quadratic model. And it's ideal for identifying relatively simple model structures in many factors. The analysis can be a little bit tricky. You have to be a little bit careful there as well. Just backward p-value reduction is not the way to go. Uh, in my objective, what I found is that Aikaiki's correction criteria works pretty well, which is also available in Design Expert. But there are some other ways in recent literature that you can analyze those. But of course, the designs do struggle with more than a few interactions if they are significant. So we need to be careful there. Typically, you've got your factors that are numerical, 3 levels, equally spaced. Categorical factors can be added on 2 levels, and you can add dummy factors to increase the number of samples, to increase accuracy, and all that kind of good stuff. Typically, the number of samples is 2k plus 1, where k then is the number of numerical factors. And depending on how many numerical factors you add, the categorical factors can add a few samples, but not more than 5, as far as I've found. These designs this is what you get, so you can't add multi-factor constraints, like you want 2 levels, 2 factors not to be above this or that. And you have to be careful that your extreme factor setting combinations are practically possible, so that when there's many samples in a definitive screening design where a few of your factors are either at the high level or at the low level, and of course that needs to be executable. In our case, in the paint example, I can't have samples that do not stick to a panel or that are too thick to come out of a spray gun, for example. So that is something that you do need to keep an eye out for, actually, to to make sure that indeed the design that you have chosen will be executable. Um, and so these are just some high level properties. It's of course not all the details, but just some ideas on what the DSD was looking to do. Now, based on this prior knowledge that I already talked about, the experience of the subject expert people, the applicators, but also prior DOEs that we've done and analysis on color, we decided that definitive screening designs is the way to go. We don't expect humongously complex models in this case. And all these combinations that I talked about are indeed doable given the ranges that we selected. So we had 9 numerical factors, so 4 on the robot for each layer. That's 8, 1 time in between layers, the time in between, which is 9. And then I should have put the dummy factor separately, and we added one additional dummy factor, which just increases the number of samples a little bit by two, to give a little bit more breathing air in case maybe something somewhere went wrong. Um, but so that's not included in the 9. I should have put that in the slide differently. And then we had one categorical factor that was the two levels, so the two types of application guns. It added up to a total of 26 runs. And of course, you might say, yeah, it's a robotic application, but it still takes quite a while to run 26 runs. So it's not like you can just, because it's robots, just add endless amounts of samples. You still need to be effective to make sure that this is done in a speedy and efficient way. And we added 5 verification runs within the design space that were based on the experience of the applicator, so of the team that we were working with. The responses, an important one is the layer thickness. The layer thickness of the robot that the robot is spraying after 2 layers should be similar to what the manual applicator is doing. And the color, of course, needs to match. That's a very crucial thing. And color is complex in its dimensions. For effect coatings, it can go up to 23 dimensions, so 23 responses. The good thing is that there's a lot of dependencies in these dimensions. Also, again, we know that based on our prior knowledge of these type of experiments. And so you already hear me say a lot, my prior knowledge of our prior knowledge, because that then allows you to go for this type of very efficient designs, which if you don't have that knowledge, you might still have to go for the 75 from the optimal design. We chose one critical base color to do the experiment with. It's not ideal, of course. I would like to do that with more colors to be more certain of what we were doing. But we had to take some risk and speed up the delivery. And selected this color because the generic idea was that if we can fix this color or get a good application program for this color, then the other colors will also follow. Of course, which is very important, whether you do DOE or any other experimentation, we have several standard methods of operation and analysis to ensure that what we do is qualitatively right, repeatable, so that indeed, if you do it again, you get at least similar results. So we've got a lot of structured way to execute our experiments and to do measurements and analysis. So just some results, not going into the endless amounts of details. Um, so on the layer thickness, which is very important, which you can measure pretty accurately, we ended up with a model of with 8 main factors. We had 3 second order interactions and 1 quadratic term. We had a predicted R squared of 97%, which is of course very good with this relatively simple model. For color, like I said, it's multi-dimensional, but we had some main drivers which we knew that we had to look at. These models were driven by only 5 main factors, with only 1 or 2 not very powerful but still significant second order interactions. Predicted R squares were all above 85%, which for color is actually pretty good. And in both models, or in all the models, the verification runs that we added were very small compared to the predictions that the models gave. And this is a very nice feature in Design Expert, where you can highlight a few of the runs as verification runs. They are not included in the model build, but they are then, for example, shown in the graphs, and you can do diagnostics to see how well they fit in the build models. That's really a useful tool, and especially if you do these very small, efficient designs, it's good to add them so that you can kind of verify directly whether indeed what you the models that you've created that indeed they make sense. We then did some optimization, or at least looked at the data, of course. Perturbation graphs in this case was really useful because we had kind of a standard the base program that was already created, so we can see how we could change the responses to get closer to the requirements. And it's really important because then you stay closer to what the application experts already created, and that also allows for more buy-in, of course. You typically in DOE, in this case as well, you find more than one option that will give you the requirements, but there were some other business-like needs or wishes that we could, uh, yeah, that we had to include, or at least, if possible, that we should include. That kind of made us choose a certain amount. So on the left bottom, you see a perturbation graph, which is very useful when you have a start already and you want to see how you can, from that start, move into a certain direction by changing, in this case, then one factor. Be careful, it doesn't show any interaction, so don't use it as this factor does this or this factor does that. It's really for a starting point. And in the middle, of course, you see the contour plot for two factors, for the two main factors that drove color in this case. So this was actually where we left it off. So this is what I want to also bring across is that, of course, a definitive screening design you might not find as the ideal optimization step, and that there should be a next step that you should do a zoomed in optimization design, for example. We didn't do that because we were happy with the results that we got, and we moved it into the next step. I will show that from a business perspective what needed to be done. Um, and so, given prior knowledge, experimental knowledge, both from DOE but also from other experiments, knowledge from color, knowledge from the application experts, it was not necessary to do a full quadratic optimization model and design. We could do the screening design and continue with that into the next steps of our project, basically. So, as I said, I'm a statistician by education, and I was brought up with sequential designs like Statis as this nice graph. I stole it from the Statis website where you do screening, characterization, optimization, and ruggedness testing. So that's the score. And so I started wondering at a certain point in my career, like, okay, so is this not true? Is this something that you should not follow anymore? And the answer is you certainly have to follow this. But you sometimes need to consider other information with it, like the prior knowledge, fast first expert trials to kind of come close to 80-20 and then optimize using DOE with efficient designs. In my business, there's a lot of curvature in our relations. So I'm not a big step fan in this separate characterization optimization, but definitely separation of yeah, types of designs is humongously important. That you don't try to solve all the problems of the world in one go and confuse a lot of other researchers or the chemists or the physicists that might be in your company. Um, or even run into problems with an analysis when you try to combine screening and optimization, or humongous high fifths if you have very different ranges in your mixture design. Um, so, but it's not as fixed in stone to exactly follow these steps. There should be freedom based on the additional information that you bring to the table. And always remember, as George Bach said, that all models are wrong and some are useful. So don't overestimate sometimes the need for the exact theory behind every experiment that you do. As long as you know the risk and understand what might be going on, it's good. Because, of course, in this case that we executed, it might have happened. It could have happened that indeed the definitive screening design did not give the required information or had low R squared or bad verification residuals. Then we would have followed up, of course. So DOE is the goal. It's not the goal. It's also not the end point. So in this case, we had a practical challenge to optimize the application program. There were practical restrictions on the solution, and we could already start with a good base program that was developed by the applicators, the paint color experts, and of course a lot of prior knowledge. Then we have design of experiments to add the understanding what drives the critical responses, which then, of course, if you do it right, will get you the fast and efficient, and which is very important in my business and maybe in others as well. A big example, a big advantage of DOE is that you don't get the "Did you try this?" question. If you do OFAT or just experiment a little bit here and there, or do black box stuff, you get a lot of okay, yeah, this looks good, but couldn't we improve it further or what? With DOE, you can show, look, we found the sweet spot or the sweet spots, and we selected one of them. within the ranges that we've tried, the experimental design space, this is it. And so there's a big interaction between the expert knowledge people and the DOE expert to understand what needs to be done to come with the most efficient experimental strategy. In this case, we were not done after the definitive screening design because we had to prove that the solution we found was good in a standard test setup. So we had to apply it, test it over a larger set of colors, which then had to be assessed by expert and measured with the spectrophotometers to see how it performed against a benchmark product program, something that we already had in the market for quite a long time, to make sure that we're not over asking uh, from our new development or underperforming compared to the work that we already had, the products that we already have in the market. And then next step is to integrate it in the process. The program needs to be approved by the management, by the product managers, and by the project managers, and then the program will be rolled out. The application program will be rolled out in all labs. And to do that, you also need some buy-in from the management in the approach that you followed. And so just teaching our researchers, our chemists and physicists about DOE is typically not enough. You need to get that indeed the way of experimenting is supported and that they don't ask for endless amounts of samples to show something that can be done much more efficient. So just reflecting a little bit is that indeed in this example, we got to the optimal robotic application program for our new product. We did it in a fast and efficient way, and we stopped most of the discussions. There's always a little bit of discussion afterwards, but that's in any business. Um, and so what I kind of want to give based on what I was saying is that you need to look at DOE more like a tool, like a collection of tools, like the craftsmanship tools that you see on the right, and you select what you need to get the job done. It's not always that you always use the same tool from the DOE box. You select what you need. You keep it up to date, new designs, new analysis, new graphs, new design expert um, versions. It works the best with multiple disciplines together. I can't DOE a new product, but DOE helps to speed up the process, use each other's expertise and use prior knowledge, both from the product but also from DOEs. So from DOE knowledge, but also from previous output of DOEs. Because in this case, the fact that we knew how color and application were kind of relating to each other already for other products, the DSD became an option, because otherwise we would have had to have gone for the larger design or reduce factors, of course. And just remember that theory never got a screw into a wall either. Theory is great, but it needs to work. You need to get in my case, the scientist and the physicist, the chemist, uh, engaged and show them what it can do in the most efficient way. If you give them a DOE and send them off with 54 samples to make in a lab for 4 factors, you're going to lose them. That's not going to work. You need to do it in the most efficient way and keep working to drive efficiency even in DOE. So with that, I want to thank the Statis team for giving me the opportunity to present. I'm still hoping for a face-to-face meeting in 2026 because, like I said, it's very useful before the COVID period, the user meetings that we had. And of course, it's much more nicer to talk face-to-face than over a screen. Um, and I'm looking forward to the next sessions also on Friday, at the last day of the summit. So have a look at those as well. I will certainly do that. So thanks a lot, and if there are any questions, more than happy to answer them.
Thank you, Niels. It's a very thorough and interesting presentation.
Thank you.
I learned a lot more about coatings than I thought I knew. So anyone who does have questions, go ahead and put them in the chat or the questions section. We have a question about, can you explain more about using prior knowledge?
Yeah, so I can a little bit. In this case, as a prior knowledge is case dependent, but before we did this work, like I said, I've been with the company for quite a while. We did several other studies into how application parameters impact color, layer thickness, and other properties. And based on that, you see certain directions appearing in which type of models, how complex they are, which factors, do you need a lot of interactions, which responses are the most relevant ones. And that helps to kind of zoom in on the designs that you needed to do. So that really helps. Like for example, for color, we know that not all of the application parameters that we were changing were very likely to impact color. And so we were kind of aiming for in color for a low number of significant factors, which the definitive skinning designs can really nicely work with. So that's from the DOE perspective, and of course, knowledge in color, and especially in color, how that relates, what do we look at, helps to also know how accurate, for example, the models will be. So that's more the prior knowledge based on previous experiments to kind of learn from the previous experiments, whether they are DOEs or not sometimes, to use that input to drive your next experiments in a more efficient way. Hope that helps.
Thank you. Our next question is, how did you select important two-factor interactions from a DSD analysis?
Yeah, so um, so what we typically do, there are separate ways of analyzing DSDs. It's literature on that, but what we typically found, because what I then do is I recreate the designs, for example, that are listed in literature and see how I can come to similar models. That the Ikaike's criteria forward selection is a really good tool for DSD designs to come with a first indication of which model terms are significant. And so that will identify, well, at first glance, the most important design, yeah, model terms, and that can also include second order interaction model terms. But of course, you got to be a little bit careful there, because if you find many, that is really tricky. But if it's only a few, then that might actually yeah, give you the right direction. The next step that I always do is start the design with the main effects and the quadratic terms, see what that brings. And if that is, if the model with the second order terms is actually very close in performance to the one with only the main effects and the quadratic terms, then of course it might make sense to just decide that the second order interactions are just, yeah, are, although significant, are not relevant. Um, but so the Ikaike's criteria forward selection that is available in Design Expert does give you the indication of the main second order interactions if you have them. But you have to be very careful. So if you find many, you might have to consider adding samples or yeah, moving into more optimization type designs. But so this, we knew that the chances that that would happen were low given the prior knowledge that we had. So this is really linked to each other indeed. Yeah. But it's kind of like any analysis of a DOE, especially the more complex designs or sometimes more complex responses. That just doing one type way of analysis, like a backward p-value selection, for example. Yeah, you've got a little bit careful with that to avoid overestimating. So one of the more uh, rigid methods, like Ikaike's criteria, for example, or the BIC, makes definitely sense to do. I have to admit, I don't apply the proposed more complex analysis methods in literature, um, but I did some testing against what kind of makes sense, how you get to the same results. So that gave me some trust that what we found was good. And of course, the verification runs, that is important, because indeed that will show you whether the model that you have created is not over predicting, or that are model terms that are really not relevant and just popped off as significant. So it's not as simple as just doing a backward selection or something like that. You need to dig into it a little bit more. Um, and like I said, the whole prior knowledge thing to actually select the design is very relevant.
Thank you. Next question. Is DOE sometimes coupled with Bayesian statistics as another way of using prior knowledge?
Yes, yeah. That's I have to admit that so as you could see, I have been I was brought up with not with Bayesian statistics, I have to admit. And so now in the company, over the years that I was more in management over the last few years, we have developed ways of working with Bayesian statistics as well, um, in the more in a more structured way. We have people looking into that, what that brings, in which cases it brings additional information. So definitely we are using that and looking into that. In this case, this is also from like 2 years ago. We didn't do that, but it's definitely something that we're looking into. And on Tuesday, I asked a question as well in one of the sessions. That of course there is this upcoming question about DOE versus Bayesian, AI, ML. There are all kinds of companies that make statements that they can do things so much faster than DOE. Um, and I think the goal should be to combine the tools. Like I said, for me, it's more like a toolbox to solve problems. And so by combining these toolboxes, I think we can drive efficiency even further um, than just by using DOE, for example. Yeah, so in short, we are looking into that and using it already, but it is something that is growing in the company.
Okay. Next question. You indicated that in your case study, the definitive screening design was sufficient, but in cases where it is not, if you ever run into that, is your next step then to run a full quadratic model, or would you change your setup for a DSD somehow and run it again? Or is it your
No,
experience that DSDs always work?
yeah, no, definitely not. So no, it's not that it always works. It of course does help that you think about it properly up front, so that will increase the chances of that it will work. It's not that we just throw DSD at everything that we do. That's definitely not the case. For sure not, actually. Also because of course the DSDs cannot handle more complex design spaces, and that in many of, for example, formulation stuff, the design spaces are more complex, and so these would never work. But if in case we've had it once or twice where it turned out, like that refers to the question earlier, that you do your analysis and you see all these second order stuff popping up, you're like, ooh, that's not good. Then you need to um, what we did in that case, indeed, we moved to full quadratic. Um, we did do, because that was quite a lot of experiments. So we decided to do some screening um, responses first, so not do full response evaluation of the responses that were in the end after. So we kind of stepped away from it, did a little bit of screening, and then moved on. But so then you need to act, and it can be that you have to go full quadratic, but you could also, if there's an indication of certain model terms, you could augment your design using Design Expert, for example, to include those, well, possibly significant second order interaction terms. But there again, always use verification runs as well to see if that would work, if that kind of gives the right result. The safe bet would be to go full quadratic to augment your design, because you can do that in Design Expert. You can take your current design as you already did, and then with a block structure, add additional runs using the software. The software will suggest which runs you need to do, so you don't have to start from scratch. So that would be an option if you really see that you, yeah, let's say, underestimated the complexity of your challenge. Definitely. Um, so yeah, it has happened for sure. But I think the important thing is, like, that's why it's called design of experiments. The design part is very important. So to think more about not just what DUV tells you, but also indeed what the history of experimentation or the subject matter expert told you, to reduce the chance that that will happen. But yeah, it has happened, and then you expand, augment the design to the requirements that you need.
All right. Is there a DOE educational program within AkzoNobel? And can you give some details?
Yeah, so in AkzoNobel, in the past, we had DOE courses, which I was a big part of. Um, and those are still running. We've changed a little bit in the setup because, of course, all the online stuff which kind of came up during COVID. But yeah, we have a program on DOE training, um, and we also uh, try to, but that's more local. I'm working in the Netherlands, where we have a big R&D hub. There, when, for example, interns come in, they typically come in the beginning of the school year, so around September. We give them an introduction into a high level introduction into DOE so that they kind of understand why we do certain setups the way we do. We don't go in a full fledged for them. But yeah, there's definitely a program, and that program is highly tailored towards coatings industry. So, you know, we will touch on factorial designs, but most of the stuff that we do is response surface mixture and effective screening designs that we're looking into. So it's highly tailored towards yeah the material that we are working with. For example, um, we have then we're working to speed that up again to also do some more more complex topics like, for example, split plot designs, which sometimes also is something that we have to deal with. Uh, so we have a program running, and we're actually looking to accelerate that again in the company. But it's not a standard basic DOE program. It is really tailored to the type of work that we are encountering where we can use DOE optimally.
That sounds very helpful. And if you don't have one of
Yeah,
these in your organization and would like to, Staties does come in and run industry specific courses as
yeah,
needed. And I know we've taught a
yeah.
couple at AkzoNobel, but probably
Yes,
not since we
definitely.
got,
Yeah, yeah, for sure. Yeah, yeah,
yeah.
yeah.
So I think we've got our last question here. How many confirmation runs do you need, and do you use them afterwards to fine tune the coefficients of your models?
No, yeah, that's a good one. So in this case, we did five. That was based on the base program that experts created and four directions in the vectors that they thought would be useful. So we kind of said five. We, I don't have a fixed number or a recommendation. Um, from a testing perspective, but that's not really the full goal of DSD, of course. You would I kind of was taught in university that you always need to have kind of 8 spare samples to test against. And so that's kind of always my magic number, but that is more based on what I was taught at university a little bit to also to keep some spares that if you drop something. Um, so when we already did the dummy factor, which added 2, and then we decided on 5 verification runs. Yeah, that's not scientifically based. That's more what can we do, and what kind of from the discussions with the experts came out. So that's why we had 5. There's no really scientific thinking. Like I said, except for yeah, in my head, everything needs to have like 8 additional things to be able to have some meat on the bone and to test against. Um, what we did, so what I mainly focused in the analysis is to use the verification run setup in Design Expert. So you build your model on the designed runs, so the 26 from the top of my head that we do, and then the 5 are identified as verification runs. So then the model is built on 26, but in the diagnostics and the residual analysis, you see the 5 visually and also numerically in some of the overviews pop up to directly see whether they fit or not. Um, and if they do, then I'm not going to re-estimate the model because in my belief, the design is the design. And if the verification runs fit, then the done is right. If the verification wouldn't fit, well, then of course, then we got into the other question. We might have to look into whether we had the right model and the right design. But so no, I then leave the verification runs out and don't adjust the model back to include the verification runs. So I just use them as verification runs, not to update or upgrade the model at that point. No.
Okay, well, that is time. Thank you very much, Niels, for an informative and productive session. This will prove very useful, I'm sure, to many people. We
Thank you.
do have, if you would like to connect with Niels, do you have contact information you'd like to hand out?
Yeah, you can. Well, I'm on LinkedIn. Sorry, in my bio on the that we submitted for the studies, so it's probably there. There is my link to my LinkedIn, and you can always drop me an email. It's very simple. It's my Niels.Dekker, so it's on the first slide with the dot in between at AkzoNobel.com. So you can always drop me an email. More than happy to help out. But as I said, the bio gives more information.
Wonderful. Well, I hope to see you all tomorrow for our last two talks. And thank you again. Happy
Thanks.
40th to Staddies. Happy 100th to DOE. And have a great rest of your day.
Thank you. Have a nice day. Bye bye all. Thanks.